So, in the last hour, you got a taste of all that's involved in making this incredible discovery that was made. Now you'll get a taste of something else, which is interesting to me as a scientist, and that is we go back and forth between kind of theoretical ideas and experimental measurements. You saw it in the last one. We had a theoretical idea that came along in the 1960s. By the time the experiment came along, almost everything that had been done in between reinforced that idea. And but we didn't know enough about it, where to look, and it became more or less a challenge, a big technical and data analysis challenge to be able to see something. Almost in parallel, another theoretical idea was developed, and we're going to trace that. And since this course is about frontiers, you're going to see kind of where we run into a wall and can't tell something. This idea is called supersymmetry. And today we don't know whether supersymmetry has any reality. And in fact, I think the evidence is that if you weren't prejudiced strongly that it should exist, you'd be pretty well convinced that it probably doesn't. And so this is a good example of kind of, and I'll show you why people love it so much and why maybe our picture of the way nature isn't always borne out. That's why we need both experiment and theory to understand science as we move forward, whether it's physics or chemistry or biology or anything else. We need to verify what really happens, and sometimes we see things that we didn't expect and then have to explain those. Supersymmetry is an idea that developed and had a huge following, enormous number of papers of all the consequences of this theory, and a huge disappointment now that at this point it hasn't been seen, and I'll show you that. I'm not going to concentrate so much on the experimental stuff because they're negative. One of the most, maybe the most respected theoretical physicist today is a physicist at Princeton named Ed Witten, and who's developed most of the ideas, many of the ideas, especially mathematically, in string theory. So he's kind of the main person that's developed something people have heard of, string theory, which I'm not going to talk about here. But he is quoted here as talking about supersymmetry, and it again shows an attitude towards supersymmetry that here one of the most respected people in physics says. So he says supersymmetry, if it holds in nature, it's a good thing he uses if, is part of the quantum structure of space and time. A discovery of supersymmetry would be one of the real milestones in physics. Indeed, supersymmetry is one of the basic requirements of string theory, reasons he wants it. But notice requirements. So if there isn't supersymmetry, does that mean we throw away string theory? We're not sure. Discovery of supersymmetry would surely give string theory an enormous boost, and the search for supersymmetry is one of the great dramas in present-day physics. That's a good introduction. What's the idea? The idea of supersymmetry we can trace back basically to an idea that we use a lot in physics and quantum mechanics and so forth, often referred to as Noether's theorem, and that is that symmetries, invariances if you want, in nature naturally lead to things that are conserved, and conservation is something that's basic in nature. Conservation of energy, we have a certain amount of energy around. Conservation of other features, linear momentum, angular momentum, energy conservation, and so forth. So this is not unique, that when we pick supersymmetry here, that symmetry is something that's worked extremely well as a guideline to describe nature. It works obviously visually. You look at snowflakes, they're symmetrical when you look at the way they're constructed. almost everything in nature is symmetrical. Not everything, of course, but most. And usually we pick on the little bit of asymmetries to understand things. The one that we'll talk about more here, and I've mentioned before, is the asymmetries, for example, parity. When you look in a mirror, do you see exactly a mirror image of yourself, or is it slightly different from each other? And in nature, there is some difference, and that taught us a lot about weak decays. So when I talked about weak decays, we had something called parity violation. That's one of the rare cases in nature, we do have them, where symmetry isn't there. So it's a big ingredient in the way we think about nature. But what's not just symmetry, but supersymmetry? There are two types of particles in nature. I've shown you those. We call them fermions and we call them bosons. The difference between the two is this quantum mechanical feature that we call spin. One, the fermions, which are the quarks, are the fermions, have a half a unit of spin, and the bosons, 1 unit. And that's basically there, and you don't have to understand more quantum mechanics. It's just a feature of quantum mechanics. So fermions, as I said here, have the half unit. They tend to have features because they have the half unit, which is illustrated in the picture here, that they always like to stay, for example, apart from each other. So in this illustration, they would want separate rooms. Bosons, on the other hand, are the ones that have zero spin or integer spin, and they like each other, so they like to share or be together. So in terms of kind of a macroscopic view, they would like to share. Supersymmetry says that for every fermion in nature, the one kind of particle where we've got all these like quarks, for every one of them, there's a boson. And for every boson, there's a fermion that has the same feature. So another symmetry in nature, that we have all the particles shown in the upper half here, and that there's a mirror image of them with the opposite nature. It'll be the same particle, but rather than have a half integer spin, it has 0 or 1. So there's a particle just like every one that we have, but it has the other spin. And that's a bigger symmetry in nature. People like that idea, but I'll show you some of the consequences as we go along. So finding symmetries, as I say, become kind of a guiding principle. When we don't know something about nature, one of the first things we look at is whether the way we're thinking about it is symmetrical or whether there's symmetries. So supersymmetry is simple. It's just a proposal that for every spin a half fermion, that's the quarks and the leptons in the pictures that I drew for you, there's a spin 0 boson that's a partner of that. Other features other than the spin are the same. For every spin 1 boson, there's a partner, which is spin a half fermion. So somehow, all these particles that I showed you, we've missed half of them in this idea. It sounds absurd, but we've missed half of them. There's another particle for every single one. There's another particle somehow. They were all different from each other, but there's some particle. But the masses of these particles, because that's done in a different way, might be very different. They may have nothing to do with the masses. So we've made them symmetrical. But one thing that isn't symmetrical is the masses, because mass is created in a different way. So the reason we haven't seen them, presumably, in the story, is that we haven't seen, we don't know what their mass is. We have to look for the particles that have mass. The general approach is to try to find the one that's the lightest. It should be the easiest to find. But we're not sure which is the lightest. Do they necessarily follow the same mass pattern as regular ones? So that's even in itself a question. So if I drew the picture that I drew, the standard picture, it's the left-hand side of what I show up here. And now the hypothesis is there's a whole set with one change, and that is their spin of a mirror of every one of these that should exist in nature, and we just haven't found them. We haven't seen them. And they're given a name. Since they're supersymmetric particles, you just put an S on the front. So a quark's partner becomes a squark. Lepton's partner becomes a slepton, and so forth. And this is generally called SUSY, which stands for supersymmetric particles. So that's the game, and they're all given these names. And I would say that it was at least as expected when CERN turned on that you would see supersymmetric particles as Higgs particles, and maybe in some ways more of an investment in it because there's so many consequences that people had predicted. So let's look at this. So we have what I've shown you before, although we haven't really talked much about the neutrinos. They're the most interesting, actually, yet. We're going to do that in the future lectures. This is what we have. These are the particles we have, and now we're going to hypothesize that we have a whole set of other ones that are the S matters, are supersymmetric matters. And they're, in quantum mechanical terms, they're spin zero bosons instead of spin half fermions. Okay, so the bosons we have are the force carriers. We've had 4 different kinds of force carriers. We have gravity. Maybe there's a graviton. When we come to talking about gravity, we're spring. We haven't seen a graviton. We're not sure it exists. It doesn't fit in necessarily except by symmetry. The weak interactions, I spent the last week or so showing you there's these heavy particles that are responsible for that. Charge one is the W. There's a W plus and a W minus. And the other one, which is neutral, is called the Z0. And if you remember, they have masses of about almost 100 times the mass of a proton. So they're very, very heavy. The fact that they have a mass that's so heavy, and we work with different mass scales, it turns out the consequence of them being so mismatched in mass is why the weak interaction is so weak. Then we have the electromagnetic interaction, that's the photon and electromagnetism, and finally the gluon, or the strong interaction. Now we hypothesize there's supersymmetric particles, or SUSY, and now there should be a force carrier for each of those. So we should have a gravitino, partner for the W and the Z, a photino, and a gluino. So in addition to the new particles, we have new force carriers. And that's all symmetrical, and that's the idea. But we haven't seen any of these, keep in mind, and yet there's thousands of papers written on various consequences of this being in nature. And I think for many physicists, it was just assumed that this is true, and it was worth spending the time figuring out the consequences, even if we haven't seen it. Now we have to question whether we've seen it or not. So even the Higgs boson that I talked about, there'll now be a Higgsino, so there's something else, we just haven't seen it. In SUSY, we duplicate all these, so that's it. Why is this so attractive in the beginning? It's attractive for various theoretical reasons, and I'll show you that it's pretty compelling that it's there. The first one is interesting, and that is, and I don't even, I think, show this on this plot because I'm sticking with particle physics, but in a sense, there you could think that supersymmetry, if it exists, solves not just one of the biggest problems in particle physics, but the biggest problem in astrophysics. And that is that it presumably could be the dark matter that we're looking for. And that was a big reason that people like the idea. There's good evidence when we talk about astrophysics that the dark matter is particles of some sort, but not ordinary particles. And we'll talk about the evidence for that when we talk about dark matter. It may be, again, we're following a trail that's wrong, but the general feeling of what dark matter is, the general thing about dark matter is we have gravity and there's more pull than the amount of matter that's out there. But then when we look at it in more detail, it appears that the matter that's out there isn't normal matter. It's something about it that's different. So a prime candidate is matter that we haven't seen yet in particle theory, and that would be supersymmetry. We don't have many cases, I think, where maybe the biggest problem in two fields gets solved with one solution, but supersymmetry has that attraction. If it were found at CERN, it very likely would be the dark matter that we're looking for so hard in nature. It solves a whole bunch of problems in particle physics, if it exists. First, when we take this standard model and we look at it and try to calculate things, there's a lot of ugliness in the calculations, a lot of what we call fine-tuning. You have to make cancellations, so there's not infinities theoretically that are odd, and it is an ugliness of the standard particle model that we've looked at the last weeks and grown to love, that it has intrinsic problems, that it has cancellations that are very difficult. You have to kind of tune them out. And instead, if you have SUSY and it existed, it makes these cancellations happen pretty naturally. So that solves a deep theoretical problem. So I've given you two things already. Maybe the dark matter, one of the theoretical uglinesses of the standard model, gets solved by using supersymmetric particles. I said this, it could be the dark matter. It also could explain inflation. Inflation is the fact that early after the Big Bang, there apparently was a faster than expected expansion. And that faster than expected expansion is given a name that comes from economics, if you want, inflation, that things start going away from you. And so that's pretty much another pretty fundamental problem. We don't understand inflation. It's empirical, that our best picture of the early universe, when we come to it and I show you, is that there's inflation. This might explain inflation. So supersymmetry has all these attractive features that it could describe this. People develop different models of it that have different consequences. So for example, I give an example on the bottom here, a version of SUSY in the standard model that has an extra Higgs that maybe we haven't found yet. We found one, but it doesn't mean there isn't a second one, can be used and made into a picture that pretty well describes this inflation that I talked about. So lastly, almost the biggest problem we have in physics is to somehow try to unify all these forces. So let me show you a graph, and it makes it incredibly attractive that you would have nature have this theory. So what happens? Everything I've talked about in this course so far is shown on this graph as these interactions, strong, weak electromagnetic interactions, and we're at energies that are down here, where we can attack them on an accelerator. The energy where we expect that there might be what we call unification is way up here, about 10 to the 15 GeV. We're only able to explore down here. So we explore down there, and then we extrapolate, and what do we get? These reactions that I talked about so far, I've shown here in the best way we can determine them. I've shown you a lot of data to measure the electromagnetic interaction, the weak interaction, the strong interaction, and something about their behavior by looking at it at different energies. And then you can extrapolate it to where in nature, if there was grand unification, they should have the same strength. So when you come up to here, these should come together in a point. They don't. So they're not far off, so it's tempting to think that maybe we're not doing the extrapolation quite right. And in fact, if you add and say there's supersymmetry in nature, this is what you get. So it's easy to take supersymmetry and see that these forces come together, and although we don't have a theory for it yet, that in nature there is a unification of all these forces, something that theoretical physicists have tried to do since the time of Einstein. So I've shown you a whole set of incredible problems that we make big strides to solve, that could be solved assuming supersymmetry exists. So all we have to do is take this new accelerator, turn it on, and see supersymmetry. Problem is, we haven't seen it, and I'll show you the data, which is pretty impressive. So we were looking for these different particles, which I've listed here. And I think I said enough about that. So let's talk about it experimentally. So we have some other places where we can try to test things. Differences between normal particles and SUSY particles. We'll talk about a lot of these when we talk about the weak interaction. Whether there's conservation of what we call the number of baryons around or the number of leptons around. There's certain conservation laws that I'll be showing you when I talk about neutrinos. And I didn't do that when we did about the hadrons. So we can look at all of those. And in this case, we combine with that what we think is the lightest, LSP means lightest supersymmetric particle. And you'd expect, naively, that the lightest one would be the one that's coupled to the lightest particle. The lightest particle is the neutrino. So what we generally concentrated on when we look for supersymmetry is the neutralino, the neutral weakly interacting particle. It might not be the lightest one because maybe the masses go differently for the supersymmetric particles. It's not required, but it's the most attractive one to start to look for. And so it would have certain features. So supersymmetry also has glue, like the glue, so we can look for gluinos. So far, there's no significant signal for the neutralino. There's no significant signal for the gluino. There's no significant signal. These are graphs showing this, but I'm not going to bother to show you the details of them, out to quite high masses. So these are limits on production of the glue, a partner of the glue, the partner of the neutrino, and they're all null and go up to about 2,000 GeV, 10 times the mass of the Higgs particle. There are arguments that you can make that it can't be too heavy. I made the argument that they can be different from the other masses. We don't know how to make those, but there's other arguments that I'm not going to make for you that it can't be too heavy. They can't be too heavy. And in general, it's hard for them to be much more than 1,000 GeV, a TeV. And yet we have limits now that go beyond that for most of these. This is just the data, which I won't go through, for the different possibilities. The possibility that you have the partner of the top quark being the T, wiggly T, or the neutralino. So all of these have been searched for one by one at CERN, mostly at CERN. And so far, there's an incredible amount of data, incredible number of experiments, and I'm just going through them, showing each one of these pictures is several papers in the journals, and they all look at the different possibilities. This is the chargino, the neutralino, all these different particles. There's just no evidence for anything, and these are the limits. So all the possibilities, and you can see it's so small you can't read it, are shown over here, that you find something with supersymmetric qualities. The line going this way, the color, is that they're ruled out as long as they're solid color up to some mass. And these basically, our feeling was it had to be less than 1 TeV. That may be wrong, but for reasons that are pretty good, we expected that it can't be more than about a TeV. And you'll see there's nothing on here that is much, where its limits are much below that. So at this point, we basically have eliminated supersymmetry as a viable, real way nature behaves, despite how beautifully it would fix so many problems of particle physics and even astrophysics and cosmology. And that's, I think, a good illustration that we can dream, theorize how nature is, but nature is whatever it is, we have to find out about it. So this has been an incredible journey to be able to look for Susie. Of course, maybe it's still hidden and we'll find it in the next few years, but the odds of finding it are getting smaller and smaller. And so all the problems that I said, which aren't solved by this, are going to have to be solved in some other way. Why is there inflation in the early universe? What is the dark matter? So forth and so on. So that's basically where we are today at CERN or in particle physics. I'm just going to flash at you the ideas now for moving on in particle physics as a kind of an end before we go on to talking about the neutrinos. So we've talked about how accelerators work, and so I'm not going to do that. I just want to give you some sense of what the leading candidates are before in the last 5 or 10 minutes for going to yet higher energy, which maybe you'll find supersymmetry at 2 or 3 TeV, but we didn't find it at lower energy and so forth. This graph here basically shows as a function of time for colliders, for beams that are colliding with each other, how we've increased the energy with time. So, and this is a log scale this way and a linear scale in time. So it's been impressive that we've been able to go up. Probably because of technology, it's not going to go as steeply, but we have the technological ability to go to yet higher energies on this scale. The reason why it will happen or won't happen is the practical reasons of the size of accelerators, the cost, and the motivation. So not having seen anything like supersymmetry, are you sure you really want to pursue that higher energy or not? The reason to do it is kind of to follow not just supersymmetry, but are there partners, for example, of the weak boson, the W, the Z? And so you can search for that at yet higher energy, and this just shows as a function of energy that you could look for those kind of particles. When we get to neutrinos, you'll see that we have again a puzzle with neutrinos, and that is all neutrinos are like a screw. A screw goes you screw it into a wall one direction. In fact, they're all left-handed. They all screw this way. And we don't really understand why neutrinos, which I'll talk about, are all left-handed. None of them go right-handed. And so there's a lot of reasons why you could think there are right-handed neutrinos, but we haven't seen them yet, and we need a higher energy accelerator to see them. This is previewing something I'll talk about in the coming weeks when I talk about neutrinos. So there's would be right-handed neutrinos, but we haven't seen them yet. You might remember that I showed you a pretty impressive graph that there are no more neutrinos. So if there are right-hand neutrinos, they must be heavier or different in some way that we're missing those. Because I showed you the fact that the width of the Z itself implies that there's only 3 families of neutrinos. That means 3 neutrinos that are at least lower than half the mass of the Z boson itself. So anyway, that's a second one. And to do these, we have several different competing proposals, I'd say now, for where the science will go. One is called the International Linear Collider, something I helped design. And the idea there is to not have a circular machine where the electrons radiate all their energy away, but a linear collision of 2, electron and positron. That means you can go to higher energy without all this radiation that you have In a circular machine, the problem is that you need only one collision, one time they come together and then they're gone. So they have to have a high probability of collision, which means you have to focus them to very good accuracy. And then it's like two bullets shooting at each other and you have to hit. So we know the technology to do that and have designed what a machine would look like that would scatter electrons on positrons up to any energy you want. So for example, you could sit right on 125 GeV times 2 because you have electron and positron. They come in and they're exactly the energy to make a plus Higgs and a minus Higgs. If we could do that, then you have a factory basically that makes Higgs bosons, and we could finally have a way that isn't finding this little effect in the dirt to study how mass comes about in nature. So that would be the reason you would build a machine like this. The reason electrons and positrons are a very nice way to do it is that we've seen when we have, and I showed you the pictures, the collisions of protons. Protons are made up of this complication that they have a bunch of quarks in them, and they have gluons in them. When you scatter one off the other, it's one of the gluons or quarks in one scattering off one of the quarks in the other one, and so you don't have very good handle on it. If you scatter electrons on positrons, you have a point-like particles that come in, you know exactly what the initial state is. They annihilate and all the energy goes into the final particles. So there's a big attraction in doing that, and then you can pursue whether there's, for example, small differences in this graph that I showed you. This graph now is just known to something like the yellow line that I showed you here. So in order to do new accelerators, you generally need technology. And in the case of this machine that I just showed you, the new technology is called superconducting RF cryomodules. These are superconducting RF cavities that run at low temperature that can be the accelerating elements to accelerate electrons and positrons, and that's what's built into the design. Physically, they look pretty much the same as one of these big magnets. Functionally, they're totally different. Magnets at LHC are magnetic fields that bend the particles around the big circle. These that look almost the same actually are accelerating elements that accelerate electrons and positrons in a cavity. In China, they're proposing, and China is taking on big things these days, to build a very large accelerator, much bigger than the CERN accelerator, more the size like the Super Collider was going to be in the US. And this machine would both do electrons and positrons and protons and antiprotons. They've got a design. They don't really have the approval of the government yet, but they're asking for the funding now to do the final detailed design of such a machine. This machine is about 100 kilometers in size. And this is a picture of some of the magnets that they have for that. And then there's time scale something like 2030. At CERN, they're proposing to build, maybe proposing to build, that's going under review right now by physicists in Europe, whether this is what they want. But at CERN, they're talking about building a 100-kilometer ring, like China is, with very powerful magnets that have been developed at CERN. And the size of it you can see next to the LHC, which is where we were just looking for the supersymmetry and the Higgs. A big one like this that actually goes under the Lake Geneva. So this is a big, ambitious project, and you'll have no hair or gray hair like me by the time it's done. And so that's the dream there. In the long term, and I mentioned it before, if there's to be accelerators pushed to yet higher energies, probably the solution that'll be used is to use what's called plasma weak field acceleration. And that's to excite a plasma such that you can get to much higher energies by capturing it in this plasma and accelerating it. And this technique has a lot of R&D that's needed to develop it, but is probably the best potential to go to yet higher energy rather than yet bigger and bigger rings like I just showed you last time. So with that, we'll close for today. Thank you.